Welcome back, everyone. In this video, we will be covering the second part of Lecture 12. The topic is risk-neutral pricing. In the previous video, we devised a cookbook recipe for pricing any general derivative X. There were two main steps in the recipe. In the first step, what we did was we found a replicating portfolio for the derivative X. Okay. The replicating portfolio matched the payoffs of the derivative X at date capital T. And what we saw was that the replicating portfolio was always comprised of delta shares of the underlying asset or the stock and beta bonds, risk-free bonds with face value of 1. We solved for the formula for delta and beta. We did it in a completely general context with any general payoff derivative X. The formulas were delta equals XU minus XD over SU minus SD, and beta is equal to XD dot U minus XU dot D over U minus D. In the first part then, what we did was we found the replicating portfolio. In the second step, or the second part of this recipe, what we did was we applied the law of one price. Okay. The law of one price states that the price of any derivative is equal to the price of its replicating portfolio. And so what we needed to do to find the derivative price, x0, was to just go out and calculate the price of the replicating portfolio at date 0. The price of the replicating portfolio was equal to the number of shares we bought or sold, delta, times the price per share, S0, plus the number of bonds we bought or sold, beta, times the price per bond, B0, equal to e to the negative RT. This two-step recipe is economically intuitive. It just relies on replication and law of one price arguments, and it constructs a completely free of arbitrage price. The problem with this method is that calculation can be highly clunky. For one, it's kind of time consuming to calculate this price. And it's going to be not easily extendable to multiple periods, especially if we want to write some software to do multi-period pricing. Therefore, what we want to ask is the following question: is there an easier way to price X that is both faster to compute and it's going to be more generalizable to multi-period settings? The answer to this question is going to be something called the risk-neutral pricing formula. The risk-neutral pricing formula can, at first sight, just be thought of as a simple mathematical trick, but it turns out that this formula is going to have very deep economic meaning, which is quite a surprise. Okay? To derive the risk-neutral pricing formula, to give you some spoiler alert, the risk-neutral pricing formula will be at the bottom of this slide right here, risk-neutral pricing formula. Okay. To derive the risk-neutral pricing formula, we just use a couple algebraic tricks. We start by rewriting the price of the derivative that we had in the previous slide, x sub 0. The price of the derivative x sub 0 is equal to the price of its replicating portfolio, delta dot s sub 0 plus beta times b sub 0, which is equal to e to the negative RT. If you plug in your formulas for delta and beta, what are you going to get? You're going to get x sub u minus x sub d over s sub 0 u minus d dot s sub 0 plus xd dot u minus xu dot d over u minus d times e to the negative RT. Okay. What we can do is we can simplify this a couple steps further. So suppose we factor out e to the negative RT from the whole equation, and we also start combining everything over u minus d and canceling out the obvious like terms, such as the S0. What are we going to get? So first, if we factor out e to the negative RT, it's going to pop out on the outside. Then if we start combining everything over u minus d, it's going to look as follows. It's going to be xu dot e to the RT, because this never had e to the negative RT, minus xd dot e to the RT, plus xd dot u minus xu dot d, sorry, it's cramped over there, over u minus d. Okay, and the final step of deriving the risk neutral pricing formula, which I'll put down here, all we do is we start combining like terms. We still have e to the negative rt factored out. And what we're going to do is we're going to combine the terms in front of xu and xd. In front of xu comes e to the rt minus d over u minus d. You can check all my work on your own. Dot xu minus u minus e to the rt minus u minus d dot xd, all closed brackets. Okay, so this is just a mathematical re-expression of our replication pricing formula that uses the law of one price. It's just a new, different equation to price a derivative. And so what we're stuck with right now is kind of a so what question. So we can do some nice little algebra. We can make, combine all the xu's, xd's together, but it still looks just as complicated if we look at it as this slide we had several slides ago back here. Okay, looks no less complicated than that right there. Okay. We're now going to simplify this in a big way. And this simplification is also going to have some economic interpretation that we'll learn about in the third lecture. And the way we're going to simplify it is just by doing one quick definition. And that definition is something called the risk-neutral probability of the upstate. So start by defining the risk-neutral probability of the upstate as Q sub U. Okay. Q sub U is equal to e to the RT minus D over U minus D. And what you can think of QU as is just some synthetically created probability. It's going to fall between 0 and 1. Okay? When added to its converse, it's going to sum to 1. Okay? And it's just going to be a synthetic or mathematically created probability that we have right now. We'll worry about its economic meaning later. What we just want to notice is that if we introduce this synthetic risk-neutral probability, it's going to greatly simplify this pricing equation that we had in the top slide. Okay, what we can notice in the pricing equation is that the first term is nothing more than just this synthetically created probability of the upstate, Q sub U. And the second term in the equation, next to X sub D, is actually no different than 1 minus Q sub U. Okay, you can find that out on your own. Okay, and so what it happens is that if we plug in Q sub U and 1 minus Q sub U, this is going to greatly simplify this formula into something called the risk-neutral pricing formula. Okay, the risk-neutral pricing formula is going to say that the price of the derivative x in this one period binomial model is equal to the discount factor e to the negative RT times QU dot XU plus 1 minus QU times XD. Okay? This risk-neutral pricing formula is simpler because all it basically says is that the price of a derivative, so the price of the derivative is equal to its weighted average payoff okay, where weights are equal to risk neutral probabilities, okay, and everything discounted. Okay. This formula, all it basically says right here, x0 equal to e to the negative rt, qu dot xu plus 1 minus qu dot xd, just says that the derivative price, x sub 0, is equal to its discounted weighted average payoff, where the weights are risk-neutral probabilities. Okay, right, as of right now, this is just a mathematical trick. Once we solve for QU, as we'll see in this practice problem, the pricing is almost going to be automatic. Okay, but as of right now, it's just a mathematical trick, no real economic interpretation yet. Okay, so the risk-neutral pricing formula gives us this simple recipe for pricing the derivative. Again, there's just 2 steps in this recipe. In the first step, we go out, we calculate these risk-neutral probabilities. The key one to calculate is just QU. It's equal to E to the RT minus D over U minus D. And then we calculate its converse, QD equals 1 minus QU. And then to calculate the portfolio value at date 0, all we do is we take X sub 0. This is the price we want to calculate, and it's equal to the discounted weighted average payoff with the weights equal to the risk-neutral probabilities, and the discounting, importantly, being done by the risk-free rate. It's not some observable weighted average cost of capital. It's an observable risk-free rate. This recipe is quick and simple. It works for any derivative in the binomial model. It's going to be extremely fast to compute, and it's also going to be scalable in multi-period settings. It's going to have a ton of nice properties. In addition to that, we're going to be able to attach some economic meaning as well. Okay? So to get comfortable working with risk-neutral pricing, we'll do a practice problem. I'll give you a quick minute to read the question, and then I will solve it. Okay, so let's work through the problem. The problem statement is as follows. We have Las Vegas Sands Company. Las Vegas Sands is trading at $50 per share today. Las Vegas Sands is a non-dividend paying stock. 1 year from today, there are two possible states. In the U state, the up state, the price of Las Vegas Sands is 100. In the D state, the price of Las Vegas Sands is 25. Continuously compounded risk-free rate is 10%, and there's no arbitrage. Three parts to this question. First, what are the risk-neutral probabilities? Second, use the risk-neutral probabilities to price a call option with a strike of 50 on Las Vegas Sands and a maturity of 1 year. And third, price a more exotic option, something called a root derivative with payoffs equal to the square root of the payoff of the Las Vegas Sands stock. We want to price that as well. Okay, we could just go out, plug everything into these risk-neutral formulas and be done. But for instructional purposes, I'll draw out the binomial tree so we can see what's going on. Again, two dates, 0 and capital T. Capital T is 1 again, as before. Today at date 0, everything is known. In the future, there are two possible states, U and D. Not clear what's going on yet. Okay. 4 assets in this model: the stock, the bond, the call, and the root derivative. We're just going to start by adding the stock and the bond to our model. Then we'll introduce the other ones sequentially. Price of the stock today is S sub 0 equal to 50. Price of the bond today, B sub 0, is equal to E to the negative RT. R is 10%. T is 1. This is going to be, if you look on your calculator, it's like 0.9048, somewhere around there. Okay. Payoffs to the stock depend on the state of the world in the future. In the up state of the world, it's SU equal to 100. This implies that the gross rate of return equal to SU over S0 is equal to 2. In the down state of the world, the payoff to the stock is equal to 25. This implies that the gross rate of return in the down state, D, equal to S sub D over S sub 0 is equal to 1/2. Okay. Bond has a payoff that's constant in both states. It's BU equal to 1, BD equals to 1 as well. In the first question, we want to calculate the risk-neutral probabilities, QU and QD. The risk-neutral probability of the upstate, QU, is just given by an extremely simple formula, E to the R times T minus D. over u minus d. Plug in inputs, e to the 0.10 times 1 minus d, which is 1/2, over u minus d, 2 minus 1/2. This is going to be equal to 0.403. And hence QD, the risk neutral probability of the downstate, 1 minus QU is equal to 1 minus 0.403, which is equal to 0.597. Okay, so we can add these to the model up here. QU, risk neutral probability of the upstate, equal to 403. QD, equal to 1 minus QU, equal to 59.7%. These are not physical probabilities or likelihoods of these states occurring. These are just synthetic, mathematically constructed probabilities that are going to allow us to admit no arbitrage pricing with the risk-neutral pricing formula. Okay. In the second part of the question, what we do is we want to price a call option. The call option has a strike of K and a maturity of T equal to 1 year. K equal to 50, maturity of T equal to 1 year. We can introduce this to the tree so we know what its payoffs are. The call option's payoff in the upstate is equal to the max of SU minus K and 0. This is equal to the max of 100 minus 50 and 0, which is 50. So we can write down on this slide over here, payoff in the upstate is 50. And in the downstate, what we have is C sub D equal to the max of K, which is 50, minus S sub D, which is 25, and 0, which is just 0. So the call has a payoff of 50 in the upstate, 0 on the downstate. And to price the call option, all we need to do is do a quick application of the risk-neutral pricing formula. The risk-neutral pricing formula says that the price of the derivative today, which is given by C sub 0, is equal to its discounted weighted average payoff with the weights equal to the risk-neutral probabilities. The discount factor is e to the negative RT. The weighted average payoff is QU dot CU plus 1 minus QU dot CD. Okay. Plug in inputs, e to the negative 0.10 times 1. QU is equal to 40.3% times 50 plus 59.7% times 0. Calculate this all out. This is 0 over here. The only thing that matters is this portion right here. And the discount factor. Call price is going to be somewhere around $18.25. Okay, so the call price is C0 equal to $18.25. Notice how easy that risk-neutral probability calculation was relative to our previous calculations of the derivative. I recommend always using risk-neutral pricing for that reason. You just went out, you calculated the simple probability here. This probability, along with the derivative's payoffs, are all you really need to go out and calculate the derivative price. It's that simple. Okay. In the third part of the problem, what we want to do is we want to calculate the price of the power derivative, or it's a root derivative. The root derivative has a payoff equal to the square root of the payoff of the stock. And so let's introduce that to our model up here. So the root derivative's payoff in the upstate, x sub u, is equal to the square root of s sub u, equal to the square root of 100, which is 10. In the downstate, it's x sub d, equal to the square root of s sub d, equal to the square root of 25, equal to 5. Okay. So the root derivative has a payoff of 10 in the upstate, 5 in the downstate. Note this is a just exotic derivative that we picked out of nowhere. We can now price basically anything we want using this binomial model. That's why it's so powerful. Okay, and then to find the price of this, we just apply the risk-neutral pricing equation. The price of the derivative today, the root derivative today, is x sub 0 equal to the discount factor, e to the negative 0.10 times 1, times the risk-neutral probability of the upstate, which is 0.403, times the payoff of the derivative in the upstate, which is 10. This is QU. This is XU. plus 1 minus 0.403, which is 0.597, times the payoff in the down state, which is 5. Okay, this is XD, this is QD. Okay. And what we have here is that if you calculate all this out, it's going to be that the price of the root derivative is around $6.40 or 35 cents. Okay. So the price of the root derivative is $6.35. Again, notice how easy it is to calculate this price. Okay, we just went out, we calculated a couple payoff values at the terminal state. We have the risk neutral probability, we have the discount factor. Discount factor is observable, so are the risk neutral probabilities because they're backed out or extracted from asset prices. Payoffs are known as well. You take a bunch of observable inputs, plug them into the model, you get an exact price. Beautiful, simple, computationally friendly, and as we'll see, can be extended to multiple periods. Okay, so that wraps up this second part of lecture 12. Let's take a quick break and we'll resume in the next video by linking now this risk neutral probabilities to their economic interpretation.